This is the video that goes along with PowerPoint Notes A for Chapter 14, McGraw-Hill. And we're talking about mixtures and solutions in this chapter. So when we talk about mixtures and solutions, we've already talked about those back in Chapter 2 or 3. We're going to kind of go over what mixtures are and mixtures and solutions, and talk a little bit about compounds, elements, mixtures, and all that. So if you have your video notes, that will help you because you'll be able to see a little bit better. It's probably a little hard to see on the screen up here, but I will move the notes along here as we go. So mixtures are two or more substances combined physically, not chemically. Compounds combined chemically. Mixtures just physically, and we're able to separate them physically. Like boiling water, you have salt water, boil the water goes here, salt stays behind. That's a physical means for separation. Two main types of mixtures, and these two main types of mixtures are homogeneous and heterogeneous. Homo means same, hetero means different. So when you look at a homogeneous mixture, you don't see two or more different parts. When you look at a heterogeneous mixture, you do. Hetero means different. And you see, like in beef stew, you see beef, you see carrots and peas and stew, all these different things. When you look at Chex Mix, you see the little Chex, you see maybe some Cheerios and some pretzels. Those are all different things. That's a heterogeneous mix. Another name for homogeneous mixtures would be solutions, and that's always a good question for a quiz. Two-word name for solution would be, and that's homogeneous mixture. Or vice versa. You'll be given homogeneous mixture, what's a good name for that? So you should know that. Moving on to the next page, when we get the clicker to work here. Heterogeneous mixtures. So it's going to talk to you a little bit about heterogeneous mixtures, and we'll come back and talk about solutions again and kind of all three together. Suspension is a type of heterogeneous mixture. It is the largest of the mixtures in particle size. There's a chart that you're given in class, and also have that available on the website so that you could actually compare the three different types of mixtures side by seeing them all at one time, and that'll probably help you. Most of you are visual and kind of spatial visual as opposed to looking at all the words here. So, but suspension is the largest. It does settle out over time, and it is able to be filtered. When we say able to be filtered, we make a little filter apparatus, funnel with a little filter paper, pour the sand and water through, the sand stays in the filter paper, the water goes through. So we can separate with filter. Finally, the last thing is the Tyndall effect. The Tyndall effect is where when you shine light through, you see little flickers of light reflecting. Particles of sand, even smaller particles, you're able to see that flickering light reflect. So that would be the Tyndall effect. An example of this might be when you see light coming in through the blinds. You see the sunlight, you may see little flickers of dust in it. That's the Tyndall effect. So again, look at that chart, and it's important to know those because I usually do ask you a short answer question about compare the three types of mixtures by name, by the actual size, the number size, how big they are, and by two or three other traits that we're going to talk about here. The Tyndall effect, whether they settle, whether you can filter them. The next size is the medium size, and that's colloid. Now, if you can remember that colloid goes from 1 nanometer to 100 nanometers, then you'll know that suspension is bigger than 100, and solution would be smaller than 1. So the middle range is 1 to 100 nanometers. Colloids are made up of medium-sized particles. They don't settle out, mostly because colloids are thicker. Things like mayonnaise or shaving cream, they're a little bit thicker and they hold up a little bit bigger particles. They can't be filtered out when you talk about putting them in filter paper, so that would be colloid. Now, if you look at solution, of course, the solution is the smallest of the three mixture types, 1 or lower in nanometers. Atoms, generally atoms and ions and small molecules, they do not show the Tyndall effect because light does not reflect off of the, it does, but it's so small we can't see it, and cannot filter it. Filter paper holes are about 100 nanometers, give or take, and you can get different size filter paper. But you know, things that are bigger than that generally pass right through. Or smaller, I'm sorry. Things that are bigger get trapped, things that are smaller don't. Brownian motion. Brownian movement or Brownian motion is the constant movement of particles, and if it's not at absolute zero, the particles are moving. We haven't taken all the energy out, kinetic energy, until we get to absolute zero. If it's above that, the particles are moving. This is how some of the particles are kept, the mixture particles are kept in suspension, because when they hit these particles moving, it's kind of like juggling them. They keep bouncing up again, kind of like volleyball. If you try to hit it up in the air and keep it up in the air, these particles will hit parts of the mixture and keep them up in solution. But Brownian motion is that constant movement of small parts of a substance. When we talk about solutions now, remember solution is the smallest of the three types of mixtures. It is a homogeneous mixture. There are two parts to solutions. The solvent is the part that does the dissolving, and the solute is the part that gets dissolved. In a saltwater solution, salt is the solute, the solvent is water. You can have gas solutions, you can have solid solutions. Most jewelry is a solution because it's a homogeneous mixture. If you had pure gold, it'd be too soft. That would be 24 karat gold. It would be too soft and it would bend continually. So they add some other metals that are side by side with the gold, not chemically combined but physically mixed, and that is what makes it a mixture. But it's very, very small, atom-based, and that means it's a solution. The air is a solution. It is just carbon dioxide, nitrogen, all the other argon, all the other gases just side by side bumping into each other, not chemically combined. So you need to be able to tell me and classify solutions, heterogeneous mixtures, whether they're colloid, whether they're suspensions. You need to be able to classify that, or even if it's a compound. So here's some examples. If I gave you water and said, how would you classify that as matter? You would say, well, water is a compound, H2O. It's chemically combined. Now, if I told you river water, well, then you'd have to say that's a heterogeneous mixture, because water, when you scoop it up out of the river, might have little algae and bugs and sand and whatever, and it usually, if you've ever scooped water out of a river, you know it has stuff because the river's usually moving and carries those particles. So you have to look at the context of what's going on. Some other examples, fresh squeezed orange juice. That's heterogeneous because you've got seeds, pulp, you've got orange juice. If it were a high C drink, that would be homogeneous because you look at it, you don't see but one thing. It's all orange drink and that's it. You don't see things floating in it, hopefully. If you do, I wouldn't drink it. So you should know the two parts of a solution, and you should be able to classify different matter, types of matter as are they element, compound, or mixture, and if they're a mixture, are they homogeneous or heterogeneous? Kind of look at some examples of that and make sure you're able to do that. You'll have a question or two on that on the quiz and the test. Formation of solutions. So, when we talk about solution formation, there are some things that are important. If they're not mixable, then they're not going to form a solution. When we say they're soluble, that means they're able to mix. When they're insoluble, they're not able to mix. Things like oil and water are not able to mix. When they're a liquid, we use the term miscible. Miscible means the same thing as soluble in liquid terms. When they're not mixable as a liquid, we say they're immiscible. miscible, IM miscible. And those are some vocabulary. This chapter has probably a little over half math, but there's still almost half of it is going to be terms and vocabulary. Make some good flashcards, highlight your notes, make sure that you look over those and know each of the terms. Maybe you could have somebody quiz you or test you on those, or you could get an app on your phone that would do that. Solution concentrations. So there are some important things we're going to talk about as far as concentration. If there's a lot of solid or solute per amount of liquid, then we say something's concentrated. If it doesn't have very much, we say it's dilute. Those are two important terms. And again, we know that if we're going to deal with solutions, we need to have descriptive terms and be able to talk the talk. So these are some common concentration methods that we'll be talking about: percent by mass, percent by volume, molarity, molality, and mole fraction. And the rest of this set of notes will deal with each of those. We'll start out by talking about percent by mass and percent by volume. They're both basically the same. And one of the hard parts about the problems in this chapter, not that they're hard mathematically, but that there are about 8 or 9 types of problems. And you need to know what type of problem it is that you're working with when you see a problem, when you see a word problem that you're reading. So this type of problem, when you see the word percent, then you need to know that it is percent equals in the case of mass and volume, it's the mass per volume of the solution. So this would be how much the solid weighs that you're putting in grams, and this would be how many milliliters the solution is total after you've added the solid. So this would be the grams of solute. This would be the milliliters of the solution total once you're done, times 100%. So percent equals the part, the solid that you're adding, over the whole, the solution as it's finished, in milliliters, times 100. And make sure you times 100 on your calculator. Some people say, well, it's times 100%. That means just one. No, punch times 100. And that's it on that last part. So we are calculating what percent is made up by this solute. Now, this is percent MV. There's also percent VV. When we put liquid in liquid, we don't use grams on the top. We use milliliters. And remember, you have to use small scale on these. The only time you'd use big scale is if you use big scale on top and bottom. For instance, if you did kilograms on top, you'd need to use liters on bottom. Kilogram or a liter is about this size. It's a large cube. And if you have a liter of water, it weighs 1 kilogram. Those are equal in scale. So if you have kilogram on top, you can use liter on the bottom. If you have gram on top, you have to use milliliters on bottom, period. And you need to know those. This formula is one that you're not getting on possibly useful. It's more of a logical thing. Percent equals part over whole times 100. So make sure that you review over that. And that your units, sometimes I'll give you liters or kilograms or something else. Make sure you're using grams over milliliters. That would just be a good standard for this one. Or for the volume, VV, milliliters over milliliters. They're basically the same thing. Now, on one problem on the review, I'm giving you the percent, the solution, and you need to, 100, and you're going to be solving for that value. Not a problem. It's just a different approach algebraically. You basically are solving for this. You're going to, if you use the Anderson swap, you can Anderson swap that up, Anderson swap the 100 down, do the math, and you'll come out with that value in grams. That's percent by mass or percent by VV. There are some practice problems and some problems on your review. Definitely work some of those. So we move on to molarity. Again, this one's one you need to know by definition. Molarity is moles per liter. Whenever you see big M, or molarity in a problem, you need to write this exact thing. Molarity equals moles per liter. The reason is because this gives you the template for how you're going to solve the problem, but it also reminds you, make sure you have moles and make sure you have liters. On this one, you cannot have milliliters. You have to have liters, and you have to have moles. If I give you grams and milliliters, convert the grams to mole using your periodic table and dimensional analysis, and convert the milliliters to liters. Have to have moles per liter. Instance of a fairly easy problem here, let's say we put 2 moles, 2.0 moles of solute in 4.0 liters. 2 divided by 4 gives us a 0.50 molar solution, and that's the unit is molar, capital M. So we move on, and now we have molality with an L. Now, I know that is difficult. It's what we have to deal with. This system has been in place a long time, and they didn't think about sophomores and juniors in chemistry and say we need to make it easier. They made it hard here because molarity and molality sound similar. Molality with an L, think of L for little m because that's the symbol for this one. And the little m equals moles, again, moles of solute on top, over, in this case, it's kilograms of solvent. It's not kilograms of total solution at the end. It's how much solvent are you adding and how much solute in moles are you adding separately. Has to be kilograms. If I give you grams, and I usually will to see if you're actually doing the math on this correctly, make sure you convert the grams to kilograms. If you get milliliters and it's water, remember, 1 milliliter of water equals 1 gram of water, and then you can convert grams to kilograms. So that's an important value as far as shifting between volume and mass. By definition, 1 milliliter of water weighs 1 gram at 4 degrees Celsius. 1 liter of water weighs 1 kilogram. So those are kind of crossover points. Again, make sure you have moles. If I give you grams of solute, use your periodic table, dimensional analysis, 2-step problem. 1 mole is how many grams from the chart will be your conversion factor. So that's molality. Example, let's say that we have 2.0 moles of solute in 1,000 grams of water. You'd say, okay, 1,000 grams, I can't have grams. 1,000 grams, 1,000, 1, 2, 3 places over to make 1.00 kilograms. Remember, this will help you. Grams is a small unit, it has a big number. Kilogram is a big unit, so we need a small number. Big, small, they always big unit, smaller number. So 1 kilogram is equal to 1,000 grams. So we would put 1.000 kilogram, and that's 2 moles over 1 kilogram would be a 2 molal solution. And that's the unit that we use is molal. We call it molal. All right, mole fraction. This is actually one of the easier things, but remember, it's mole fraction. On your review, I give you a mole fraction problem that has grams. What do we have to do first? Use the periodic table, convert grams to moles in a 2-step dimensional analysis problem. And once you have moles, it's actually pretty easy. It's just part of a whole. Now, it's not a percent. It's a decimal. So let's say that we had 3 moles of water. This problem on the notes says we have 3 moles of water, so 3.00 moles H2O. And we've got 2 moles of NaCl, 2.00 moles NaCl. Well, all we have to do is add the 2 up to get the number on the bottom. So 3 moles out of 5 is water, which if you do 3 divided by 5, that gives you a decimal of 0.6. 3 significant digits, 0.600 is the mole fraction for water. 0.400 is the mole fraction for salt. Now, they always add up to 1. If you had 3 parts, there'd be 3 mole fractions that all added up to 1. So, again, got practice on these. Make sure that you go through and do some of those practice. Mole fraction. All right, that finishes up that first note set from chapter 14, solutions and mixtures. Do get some of the practice problems. I've got 3 or 4 sets on my website. They're landerson.net. There's also some that I handed out in class, but you might want to try your review first and work those, and then come in and check the key. Make sure you got them right. If you get them right, then before you do the quiz, go work through some of the practice problems. Thanks for listening. Good luck.